Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day to everyone. In this session, I will just continue with the next topic for the dielectric breakdown, in which we're going to look into the breakdown in solid dielectric. Right. Okay, for this topic, we're going to look into general information about the general introduction about the solid dielectric and the problem related to the solid dielectric, which is one of the most important is actually the breakdown phenomena. And then we will look into several mechanisms that lead to the breakdown of solid dielectric, in which there are intrinsic breakdown, electromechanical breakdown, thermal breakdown, treeing and tracking and erosions. Okay, what is solid dielectric? Solid dielectric is actually, it can be ranged from crystalline material to semi-crystalline polymer. Okay, in the power system application, normally solid dielectric is referred to the ceramic insulators, polymeric insulators, silicon rubber, and also paper insulated. Okay, and this material can be blended with the inorganic fillers. Right. Okay, what is fillers? Fillers is actually some very small particle in micro scale, normally sometimes in micro size particles, which blended together in the solid dielectric, for example in the insulator, to achieve a certain characteristic. For example, it just it just additional material that been added to the polymer material, so that the solid dielectric behave in a certain condition or in the certain characteristic according to the application. Okay, we will look into okay, in solid dielectric. Okay, normally it'll be used in to separate potential electrode and the earth structure. Right? Normally, in many cases, to separate between earth object or earth structure and the high voltage or the energized electrode. Okay, the simplest example that we can see is the suspension insulator. The suspension insulator, the one that hanging in the transmission line in the transmission line, in which it will provide the mechanical strength to support the earth tower and the cable to hold the transmission line. Okay, normally it provide mechanical support, as I mentioned before, insulating string, and sometimes the solid dielectric need to be used in combination with liquid and gases. For example, is the transformer. Okay, for example, is the transformer. For the transformer, we're going to have like a paper insulated, which is a solid insulator, to wrap the coil, and then within the tank we also use the liquid. Okay, and in fact the external part of the transformer we will have a bushing which is a solid dielectric, and then that is what we classify as the combination of several types of dielectric materials. Okay, insulating, winding, bushing, and so on. Okay, for insulator, in general, we have several type of insulator, which are one of the several type of the insulator, and the most commonly used is the line post type, pin type, cap and pin type, and long rod type insulator. I will show you later in the later slide example of this insulator slide, image of this insulator types. And then normally for the insulator, for solid dielectric, it made from the ceramic, the glass, and the most recent one is the composite. Okay, what is composite? We call it composite because it is a mixture of the silicon rubber by several other fillers to have the composite, which means we compose from several type of material, for example, to obtain certain characteristics as explained before. And ceramic and glass is commonly used, the conventional insulator that been used for many decades, since 1980s maybe, in 80s, since the 80th century. So this is the most recent one and the most recent technology that people are switching to from the ceramic and glass into the composite. Why? What are the advantages of a composite? First, it has excellent pollution conditions, especially for outdoor insulators. And the other part is that it is light in weight. It is less vulnerable. So it means that it is a rubber. It's a rubber, so the breakage, the risk of the breakage is very minimal, right? In which, for the glass and ceramic, once we that could be subject to breakage during the operation condition, which might lead to the failure, right? And another things, the ceramic and glass disc, if you suspend about 10 or maybe 20 discs altogether, that can only be lifted by a crane, right? Just imagine how we're going to install the ceramic and glass insulator in the, along the Peninsula Malaysia, along the highway, in which it just on the mountain, on the mountain, and how can this crane got access to this kind of area? And I believe we have seen several videos available in the YouTube how they install the ceramic glass in this kind of area by using helicopter. Okay, in which this one composite insulator can be as low as 70% weight reduction. Okay, 70%, about 70 to 80% weight reduction, which means if the glass and ceramic insulator weight of 100 kilograms, and then the composite, the same equivalent insulator will just weight 20 to 30% kilogram. It is about that size. Okay, paper insulator we use in transformer winding, and we also use a solid dielectric in the cable. Alright, in the cable. The most popular material is that polyethylene, which is XLPE, Teflon TFE, and silicon rubber. Right? So we have the function of the solid dielectric for the purpose of insulator, and for the cable and for transformer. These are the most commonly application that been used. They are using the solid dielectric. Alright. Okay, this is example of paper insulated. If you can see, we have the coil, we have the transformer, and the winding of this transformer is been wrapped with the paper, and also we will include the oil as well. So the combination of paper and liquid. Okay, so this is an example of the cable. We have the conductor, and we have the XLPE dielectric material, in which made of polymer to provide the insulation for this cable. And we have also this one, power cable. And these are the example of polymeric material as for the insulator, suspension insulator. Why we call it a suspension insulator? Because this insulator is being used to suspend the transmission line, right? So this is attached to the earth tower, a transmission tower, and then this is being used to suspend the live cable. Okay, these are the example of, for example, the defect in the insulator. because this insulator, in simplest word, is made from rubberic material, or we call it as a polymeric. And then, okay, this is also a polymeric insulator as cross arm, and this is about the recent technology in maybe in recent decades, in which people start to use, or researchers start to think of, to provide the cross arm by using the polymeric insulator. Okay, traditionally or conventionally, nowadays we are using the cross arm at the transmission tower by using the metal, and now people are working to replace the metal by using the polymeric insulator, so that we're going to have a relatively small size of the transmission tower. So this is particularly important in the urban area, in the city area, in the compact area, in which we don't have much space, and we need to go for the compact substation, compact transmission line, and compact transmission tower. Alright, again, these are the example of the bushing. These are the ceramic pull type insulator. So why pull type? Because this insulator will be mounted on the surface of say transmission tower, say the transformer, or maybe it'll mounted on the, like this one, it mounted, and then we have the live cable, and then this is the bushing that been used on the transformer for the to provide the insulation between the line and the transformer, the winding. Okay, more insulator types of the ceramic or solid dielectric material, in which we use in the substation. If you can see here, switch gear, and we use this one, as I explained before, in the transmission tower. This is what we call it cap and pin. Okay, cap and pin is normally only for the glass and the ceramic. For the polymeric insulator, for polymeric insulator, we normally call it long rod insulator. Cap and pin is referred to the glass and porcelain. So this one been stacked. Okay, look, this one been stacked 1, 2, 3, 4, 5. We stack this insulator disc onto each other, and depending on application, this one can be 10, this one can be 20. It depends on the power rating. So they are made in the disc. So how we going to stack them? We just stack them, lock them with the metal electrode, and lock, and so on. Again, ceramic as to be used as the surge arrestor, as you can see here. These are the surge arrestor. These are the one that I mentioned before. This surge arrestor been mounted on the platform here, to handle, to provide this power cable. Okay, so this is the surge arrestor. In case that one is for protection, lightning protection, in which in abnormal case, this surge arrestor will operate. And this is the bushing at the transformer, and these are the transformer, right? So we provide the surge arrestor clamp to the power line, and before it come to the transformer, to protect the transformer. Okay, we have cap and pin at the power transmission line. This is the one that I mentioned before, made of glass. If it is made of ceramic, it will be brown color, as before, as I've shown you before. So alright, okay, now we come to the problem. Several issues related to the solid dielectric. Okay, one of the important issues with the solid dielectric is that once the breakdown occurred in dielectric, it will cause a permanent damage, and the solid dielectric need to be replaced with a new one, right? Unlike to the gas, in which even multiple time of breakdowns, the gas can regain its original properties due to the nature of the gas in characteristic, in which that one can be replenished, that one can be regain its original properties. Okay, but for solid dielectric, once the breakdown occurred in the solid, that insulator need to be replaced. That will cause a permanent damage to the insulator. Even though you don't replace it, but there will be a permanent damage on the insulator, and it will never cure. In which the dielectric, if it is a gas dielectric, it can be regained, or it can be cured, or it can be regained its original characteristic. Okay. Okay, for the same solid dielectric materials here, okay, it can exhibit, okay, wide range of dielectric strength. Okay, dielectric strength in various conditions. Okay, and since most of the solid dielectric is being used outdoor, and then the outdoor factor such as temperature, humidity, rain, the environment conditions, okay, and the voltage type, of course, AC, DC or impulse, these are some of the external factor that would influence the capacity of the breakdown strength, like the pollutions, all these environmental issues will definitely affect the performance of solid dielectric. Okay, and in nature that can cause due to the exposure to the rain and the sun, the heat from the sun, for example, environment, it can cause aging, premature aging. What is meant by premature aging? Premature aging means the once insulator been manufactured, it has a certain certain period of service, so called 10 years, maybe 20 years, but what we call as the premature degradations or premature aging means that the insulator come to the total failure or total replacement far less than far less than the original or the stated operation period or usage. For example, it been prepared for 10 years, but happen to be within a year the insulator failed and need to be replaced due to aging. That is what we call as premature degradation or premature aging, due to various factor, external factor. Okay, and then for example, okay, we have the breakdown stress here, if you can see, and working stress here. There are two different things. Working stress means that we as the operation condition, okay, and the breakdown stress is about the maximum allowable field stress or stress that is allowed for the each type of the insulator or dielectric material. For example, here air we have 24, but working stress we just allowed 1. XLPE cable is 400 before it can break down, but normally we will use only at 50. So we have multiple time of the we will use the working stress condition at far below the breakdown values, as you can see here, 440, 550, 318. Okay, so we need to obviously the breakdown, the operation condition need to be far less than the abnormal conditions, in which so that we can prepare for the worst. Okay, breakdown phenomena in dielectric is not well studied by previous researchers. However, there are several breakdown phenomena or process that certainly been agreed that lead to the failure in the solid dielectric material. They are, as I mentioned before, intrinsic breakdown. We call it intrinsic breakdown, electromechanical breakdown, thermal breakdown, breakdown due to a thawing process, and breakdown due to cracking and erosion. We will look into detail for each of these five process or phenomena that lead to the failure of solid dielectric materials. Next, okay, normally, okay, this process is we can plot the different failure mechanism in solid in the function of breakdown field as a function of time. Okay, we have the duration of process. Okay, what is meant by this graph? Okay, what is meant by the graph? If we look carefully, okay, avalanche, or we call it as this normally referred as intrinsic breakdown or intrinsic breakdown or electronic breakdown. So that will happen in microseconds. Okay, microseconds. And for electromechanical, that's happen in milliseconds. For the thermal is will take time in the to the power of 4, and thawing and chemical effect, it will take a far longer of time. So means that this failure will require a prolonged period of time. Means that with time we will have the thawing phenomena and chemical effect, including the cracking and erosions, until the insulator will failure, in which it is not like the avalanche process. This will happen at the very short period of time. Okay, and the breakdown field, or the breakdown field, for example this one for avalanche, that this will require a very high breakdown field, a very high field, electric field stress to trigger for the avalanche to happen. But for the tree and for cracking, for the chemical effect, it doesn't really need the breakdown field, because it more towards the environmental effect that will lead to this failure. Okay, electromechanical require moderate electric field that will trigger for the electromechanical failure, as well as for the thermal. So we plot as a function of time, breakdown field as a function of time, and then we will have this kind of curve. Okay, this kind of curve. So you know the reason why this is high and this is short, and why this is a lower electric field breakdown, and this one is a function of time. It is to the power of 8, right, in which this one minus 8. So we can really see the difference. Once we discuss about all of this, you can come to this graph, and then you will understand what I just explained to you. Okay, intrinsic breakdown. Okay, we call as the intrinsic breakdown if the material has no impurities. Means that is if that one is the silicon rubber, it is pure silicon rubber. There is no additional fillers added to this material. Alright, and there is no external factor, external defect. We have no internal defect, and we have no external defect. We have no additional material within this solid dielectric material, and then it is also not subjected to the external discharge. That is what we classify as intrinsic breakdown. Okay, the failure of a material, of a pure material, I would say, a pure material without external factor that cause the failure, that is what we call as intrinsic. Okay, the process for the intrinsic breakdown that happen as a function of microsecond, okay, due to the field breakdown reaching, breakdown up to the mega value, voltage per centimeter. This is the field stress, okay, due to the external factor like stress. This will trigger for intrinsic breakdown, in which the best explanation to explain the intrinsic breakdown is actually as what we can classify as Townsend breakdown. What happened in Townsend breakdown is actually the electron managed to escape away from the electron in a valence band, for the atomic scale gain a certain amount of energy that allowed the electron to escape away from this atom, and then that is called as that will trigger for the intrinsic breakdown. Okay, in practice, the intrinsic breakdown can be defined as the highest breakdown values. Okay, why highest? Okay, tell me why highest. Why we classify as the highest breakdown value is because the material now in this condition, why we classify as extrinsic condition, because this material is a pure. There is no external defect. There is no external factor, that there is no, as I mentioned before, pure, no discharge activity, and no external defect, intrinsic defect. Because of that, and if that is still happen, the breakdown still happen, the intrinsic breakdown still happen, that is why we call as the highest breakdown value. Okay, just imagine this will only happen at very highest breakdown value. Okay, with the purity. Okay, say for example we have the fillers, we have the material is impure, we have external factor like discharge activity outside, we have the defect due to environment. Definitely the breakdown for this solid material will occur at far lower value than this value. Okay, far lower than this value. Say for example, for intrinsic breakdown to happen, maybe about 100 or 1000 for example. But if it is not intrinsic breakdown, the breakdown could happen at as low as 100, 200, 500, and even 50 for example. Okay, that is to simplify or to further clarify about why they call it as highest breakdown values. Okay, as I explained before, free electron in the material accelerated without limit due to the electrostatic action by the field, electric field. So in this condition, if we going to perform the experiment, we need to make sure the material is pure and homogeneous, so that to ensure the sole factor, the only factor that lead to the failure of the solid material is the intrinsic issues, the intrinsic effect. It's not other effect. Okay, and of course it need to be tested under control temperature and environment conditions. You cannot like expose to the very high temperature, exposed to the external defect, and obviously we need to eliminate the effect of external discharge. Okay, then only we can call it as a intrinsic. Okay, there are two best model to describe the intrinsic, in which electronic breakdown model and avalanche or streamers. Okay, to be honest with you, this is just a quick recap. Those what we learn in the gas dielectric material. Researcher or what we call it as Folick has described the intrinsic breakdown into these two, has classified into these two category, like electronic and avalanche. They are the expression of these two mechanism is identical to what we explained, what we discussed in the gas dielectric. Okay, intrinsic. Okay, electronic breakdown. Okay, electronic, just look by its name, that really indicates it is electron. Okay, it is electron breakdown or electronic breakdown. We call it as electronic breakdown, electron breakdown. Why it happen is because the electron managed to escape away from the valence band. Okay, why the electron managed to escape? Because they have the gain sufficient energy that allowed the electron to escape away from the atom, from the molecular, or from the what we call it as a valence band, and to come into the conduction band. They managed to escape away from the what we classify as the forbidden energy. Means that, okay, we have the molecules and then we have the valence band. The valence band is actually the outermost the outermost band for the electron. Okay, so it is far away from the nucleus, and then once it gain enough energy, it will this electron at the outer layer of the orbital will manage to escape away. That is what we call the initiation of the process for electronic breakdown. Okay, that is electronic breakdown. Okay, as I mentioned, conduction band, valence band, and normally in the absence of electric field, electron cannot gain sufficient energy, right? Because there is no electric field. But with time, this electron can gather the energy until they have sufficient to escape away from the valence band. Eventually they will slowly they will gain the energy to lead the electronic breakdown. Okay, what is avalanche or streamers? It's simple. Just imagine it is the secondary process of the electronic. Okay, it is secondary process of the electronic. Okay, why I call it as a secondary process? What will happen after the electron manage to escape away from the valence band? What will happen? It will collide with other electron. This one will collide with the other electron, with other molecule, and this kinetic energy will impart to the other electron in the valence band, and the other electron will also manage to escape away, and we will have starts to multiple effect. Okay, that's why we call it as avalanche or streamers. 1 will collide with 2, 2 will collide with 4, 4 will collide with 8, 8 will collide with so on. So this process will lead to this avalanche. That's why I call it as a secondary process of the electronic. Okay, you can read the explanation here. During the flight to anode, for example, it will collide with the crystal lattice, gain enough energy, and additional electron will lead to the avalanche effect. Okay, similar to the gas theory, right? So even under uniform field with electrode embed, the breakdown will occur and avalanche will bridge the electrode gap. Okay, so this is the effect, the secondary effect of the electronic breakdown. Okay, electronic breakdown is electron managed to escape away, but the secondary effect from this will cause the avalanche or streamer effect in the even in the solid dielectric material, similar to what we learned in the gas theory. So the same will happen in the solid. Okay, now we look at the electromechanical breakdown. What is classify what is meant by electromechanical. Look, it's very simple. What is about electromechanical? If you can see, this is the combination words of electric and mechanical. By looking at this one, since electric is at the front, so the electric field effect, the field stress effect will lead to the mechanical effect of the solid. For example, okay, under electrical stress conditions, this stress, okay, like a magnet will pull up. For example, if we put the same pole of the magnet will push away. Similar like this one, under a certain electric stress conditions, and then that will be induced force. That force, solid dielectric material, say silicon rubber, it will slightly compress the dielectric breakdown. Compress the solid dielectric, that will lead to the compression effect at the solid dielectric. There will be a slight less thickness. For example, there will be a shrink in terms of size and the thickness. Okay, you can read this explanation. Electrical stress causes specimen to collapse. Collapse, the shrink, the thickness. So this can be due to the electrostatic stress, electric field stress by the large electric field. Okay, the voltage applied across the dielectric, the specimen compressive force due to the electric. So I didn't read the explanation for you. Okay, so the best the best to describe this is by using the Stark and Gatton analysis. So means that the exerted pressure from the force due to electric field, electrostatic field, due to the applied voltage level, this will cause a reduction in the thickness. The specimen will decrease to compressive force. Okay. Originally, okay, the solid dielectric is this one, but with the field pressure, this one shrink in the size. The distance is, for example, 10, and it reduced to 5, for example, 6, for example, due to the compressive pressure. Alright, we look a bit on the Stark and Gatton analysis to describe the substance deform. Deformation of a solid dielectric is expressed by using this formula. Okay, epsilon r, the relative permittivity of the material. Epsilon naught is permittivity of free space. Voltage applied, V is the applied voltage. D, okay, D is the reduced thickness. The reduced thickness means that, okay, why we have the Young modulus ln D naught and D. Okay, D naught is the initial thickness, okay, and reduced thickness is the final thickness. Okay, for example, if the original thickness is 10, and due to the compressive force, it reduced to 7. So means that the initial thickness is 10 and the reduced thickness is 7. It's not 3, okay? It's not 3. It's 7, the final thickness. It's not 3. 3 is the difference, but in this case, D is the final thickness, for you to understand. So this is why we classify electromechanical. So it's combination of electric field effect to cause the mechanical compressive force. That's why we call it electromechanical. Okay, and we rearrange the equations, and we'll have the applied voltage as a function of thickness, and we can calculate the reduced thickness. We know this permittivity of materials, relative permittivity of material, epsilon naught. We know the Young constant, Young modulus, and we can actually calculate the compressive force, right? Let's see, okay, and hence we can classify as maximum critical voltage. Okay, for the maximum critical voltage, we call it as Vmax, Vm equal to D, the reduced thickness, the final thickness, times square root of Y divided by epsilon naught and R. Okay, or we can classify in this expression. We just rearrange the formula. Okay, why we have this one? Okay, I don't need to explain about the derivations. Okay, this is the reason. The specimen, okay, the reduction of thickness of the specimen by 40%. In other words, there is no solution if material compressed below 60% of original thickness. Further thickness will increase the voltage, collapse of the materials. Yeah. And if we differentiate this one, we differentiate this equation with respect to D, and then the value ln D naught over D will become 1 over 2. In fact, this one is equivalent to 0.6. This is about 60%. Okay. So don't worry, we just need to know how to use this formula. Let's look at this example. Okay, sorry, example is this one. Okay, right. Okay, since we started with the specimen thickness D naught, okay, this is the initial thickness of the material. We can say that the apparent highest or maximum electric field is max before the breakdown is D naught over D, which equivalent to exponential 1 to the power of exponential 1 over 2 or 0.6. That's why we can say this function as a 0.6. 0.6. So we put the value straight away. D naught over D equals 0.6. So we put 0.6 here. Then it will make easier calculation for us to calculate the Emax, maximum electric field. Okay. If the electric field is less than intrinsic strength, further increase in the V will make the specimen thickness unstable and collapse. Okay, collapse in this condition is mean shrink. It's become thickness. Become reduced, right? And polymer, just like gas and liquid, they have their own melting point. What is referred as melting point is at the point in which the polymer start to fail. In this case, I start to reduce in thickness. Alright, let's look at this tutorial. Okay, find how to use the formula. Okay, find the voltage applied in V in megavolt that cause the deformation of 1 centimeter thickness of fiberglass composite reinforced sample to be at 0.75 thickness. Okay, we have the initial thickness and we have the final thickness here. Okay, Young modulus is given as a constant values here. Relative permittivity is given here. Use the relative permittivity of air is given here. So how to use the formula is we can voltage apply. So V equal to, we just use the formula and plug in the values, and then we'll give you what is V. Okay, we'll look at the calculation later. Okay, determine the highest electric field stress max, E max. Okay, for E max, we just simply use this formula 0.6. Why 0.6? D naught initial thickness divided by D. Okay. Okay, D naught divided by final. Okay, we just use the formula, plug in the values, will give you the answer. Okay, it's just a mathematics. Okay, it's just a matter for you to know which formula to use, which and which. Why 0.6? You know the reason, and you have other values for this one, and then you should be able to calculate the voltage and to identify the maximum electric field. These are the values and the calculations. So end up with 0.36 megavolt, and end up with we use 0.6 and end up with 38.36 megavolt per meter. Okay, watch out with the unit. Okay, tutorial 2, I think the same as work example. Determine the highest, you know the formula to be used. If this one, okay, this one, the highest values will be this one, the applied voltage will be this one. So if they ask for, the question asks for the initial thickness, you can rearrange this formula and then will give you the initial and the final thickness related. It depends to the questions, but that is how we use the use the formula for the Stark and Gatton analysis from this one. Alright, I think that's all for now. In the next video, we will talk about the thermal breakdown, the next process that lead to the failure in the solid breakdown. With that, thank you, and I'll see you in the next video, inshallah. Assalamualaikum warahmatullahi wabarakatuh.